Good evening, all. Let me just get started. So, welcome to live session number 3 for the course at Computational Fluid Dynamics for Incompressible Flows, and myself, Durga Prasad Paidi. So, this course is basically an introduction course aimed at providing the basics for computational fluid dynamics using finite difference code for different kinds of partial differential equations. The course mainly focuses on solving a given set of PDE, but using the finite difference techniques. Eventually, towards the end of the course, we will also discuss finite volume methods as well. The intended audience are the UG or PG students of mechanical or faculty as well who are interested in this, and prerequisites is the fundamental knowledge of mathematics and fluid mechanics should be sufficient for this course. In myself, I am a PMRF scholar from Department of Mechanical Engineering, IIT Madras, and my research interest falls along the lines of using CFD for understanding fluids and thermodynamics inside buildings and glazing systems. These live sessions are scheduled every Saturday from 5 to 7 pm, and the meeting link will be circulated to all the enrolled students through their registered email IDs. And live sessions will be recorded, including the current one, and will be uploaded on the YouTube channel. The slides that are presented here are also shared in the Google Drive folder. I've received a couple of mails last time, so there was some technical issue because of which the drive link was not available, but now that has been resolved and you will be able to access all the content on the Google Drive link that is shared here. If you have any queries regarding the live sessions, you can write an email to me, me22t400@smail.itm.ac.in, and if you do have any other queries, feel free to raise them on the discussion forum. You can access the discussion forum through Q&A in the main website, and all the live session recordings and Google Drive, the slides that are being discussed here will be uploaded on the Google Drive, which can be accessed from this section of the course website. These are the reference books that are there on the course website, so I would personally be using the last one for these sessions. And regarding the course contents, we have already covered in the first week we discussed about the governing equations and boundary conditions. Last week we discussed PDEs. We gave some examples of different kinds of PDEs, their physical relevance, and how they are relevant for this particular application of CFD solvers. This week we will be focusing on finite difference solvers. What are the qualifications for solvers? And a technique called finite difference method, which we will elaborate a little detail in this week. So before getting into that, do you have any questions in this particular week, or any other questions in general that you want to ask?
I mean, not question, but can you turn off your fan? The mic is little low.
Oh, okay, you're having disturbance.
That's what I
Okay.
feel, but I don't know what
Okay,
others
just
feel.
give me a minute.
Yeah, it's much
Is it
much
clear
better.
better now?
Thank you. Yeah, really good.
Yeah, thank you.
Okay, I mean, sorry, I'm not watching lectures. I know finite difference, and I'm the CFD guy.
Oh, okay.
Just wondering, I want to talk about the current session though, particularly. I seen your previous. I have attended this course in the past, if I remember right. So I was just wondering, are you going to you? I remember you usually solve the assignment questions, like you take event problem, and is that what you're going to do today, or?
Yeah, it's supposed to be more or less like that. I'll just go through a quick summary of the content that has been covered in this week, say for like a
Okay.
half an hour or so, till 5:30 or 6, and then I'll take up some problems from last year assignments. So
Okay.
to people who are attending the exam, it will be useful for them.
Okay.
So if you
Okay.
do have
I
any
mean,
other
that's
questions, we can
great.
discuss them. Yeah,
So
that's it.
one personal suggestion would be suggestion. I don't know if others know, because I see you are a PhD student as well. You must be writing some codes. If you can, if you show around some codes, that would be much. I mean, that would be really great. But if you can, that's much better. Or I'm happy with whatever you are delivering. Yeah.
Yeah, that will be done, but not in this week because FDM solvers will come in the next week. So I was planning like
Sure.
next or next to next week we can actually write up. So
Okay.
uh,
Cool.
some of
Okay.
the
Okay.
students have mentioned that they are familiar with MATLAB or something, so I prefer to go in that, or someone else is there like
Python. Py- py- py-
Okay.
into any language, but Python is much better because for MATLAB you have to pay, right? You have to pay
Yeah, there
12
is an
lakhs or
octave or
something.
something,
That's
right,
why.
which is equivalent to MATLAB. We can do in that as well.
Yeah,
Yeah, depends
Scilab is
upon
also
whichever
good.
is fine. Whichever is fine. I'm fine. Like the language doesn't matter anyways, since these are all small codes.
So I don't know if I can ask. Yeah, I can ask because we can take either time, like in the end or now. So do you do any unstructured grids? I'm not doing it, but I want to learn it. So I'm like
That is not
asking
actually
like,
part of this particular course at the moment. And even during the
okay,
towards end of it, we will not be discussing on unstructured directly.
okay. Do you do unstructured grids?
Yeah, we do unstructured gits, but part of this course, no.
Yeah. No. Just as part of research, I was asking. Anyways,
Yeah.
okay. Thank you so much. We can start.
Okay. Yeah, to quickly summarize this particular week's sessions, so the main topics are we started out with Taylor series expansions, followed by different finite difference schemes defined by order of accuracy, and then we discuss something called Taylor's table, which will be used to construct the finite difference scheme of any given order for uniform and non-uniform grids. And finally, we will discuss some important terms called errors and accuracy and Lax equivalence theorem. So I hope that you've already gone through the lecture videos. To those who are not, this is kind of a brief overview of what Taylor series expansion does. So if you have a function f of x which we are trying to find, let's say we have a domain. If it is a 1D domain, we know the function value at a given point, and we are trying to find, when we solve a differential equation, what we are trying to do here is we have the boundary condition or some initial condition kind of thing. So we know the function value at a given point, but we do not know what is it at other points. So let's say I want to find the value of function at this particular point. I do not know the function value. One way to go about this is we use a Taylor series expansion, which is we'll fix a point, the one that we already know, and then we expand the value around that particular point by some delta x, and that is given by the expression the order, or we do not consider all these terms simultaneously. So depending on, like, ideally we would assume that if you are very close to the point, very close to the original point that you have taken, then the error of you, for example, if you have taken up the first terms, the remaining terms will actually be in the, I'll just use r for the remainder terms. So these terms will have an error associated with them. As delta x becomes smaller and smaller, the power will actually get reduced, and you can approximate the actual function value at a different point with only like a fewer terms, provided you are close to your original point, or depending on the function value as well. The whole idea of finite difference revolves around this particular scheme, where instead of defining for the function, we would actually get it in terms of the derivatives. Because our PDEs are usually written in terms of the derivatives, we will try to approximate these derivatives from the function values, which are themselves unknowns. So what we are trying to do now is, let's say I have an equation something like this: ux equal to c, or basically d. Let's take an ordinary differential equation, del u del x equal to c. Instead of solving this equation analytically, in finite difference what we will try to do is write a Taylor series expansion for the function u of x around a given point, and then get an approximation for du dx. So in this case, f will be my u. So there are different schemes that we can get into. So the first one is, let's say I have a function let's say this. So my original domain, the first step we will do in finite difference scheme is we discretize the domain, which essentially means instead of solving it every possible x value, which we do in analytical solution, we first divide it into discrete number of points. So let's say these are my I minus 1, I, and I plus 1. So this first step is what we call the grid. Once we discretize our domain into several points, we get a grid, and once we have the grid, we try to find the values of function at those points, grid points. These are, let's say, fi minus 1, fi, and fi plus 1. And so ideally we do not know the values of all these function values. We would only know the values at the boundaries, which are provided by boundary conditions or the initial conditions. So what we try to do now is get some equations so that we can solve for these unknowns, and the equations will come from our governing equation, which is usually a PDE or an ODE. Like usually we start with PDE in case of Navier-Stokes or whatever fluid equations that we are going to solve. So let's say my equation has a term del f del x, or in this case, since it is only one function, function of only x, I can write it as df dx. Let's say I want to evaluate at this particular point, or let's say at this particular point. So I want to evaluate the slope of this line. So how do we get a slope of this line? Is there are multiple ways to do it. You can consider the slope of this line. So the first one is a forward difference scheme. So we approximate this, the slope of this line, which is analytical slope, to be the slope of this line between these 2 points. So you obviously know that there is an error between these two. So this line is not exactly parallel to this line. But as you can see that as this point gets closer and closer, let's say instead of here, if this point was drawn a little closer, up somewhere here, then my approximation would actually be very closely parallel to the original slope. So depending on the delta x you are going to take, that can difference between the actual slope and the one that we are going to get is going to get reduced and reduced. So the scheme that when we use this one, this is a forward difference scheme. Alternatively, you can also take a backward difference. So instead of taking the forward point, you can also take a point one behind this one, and then take slope between these 2 points and say that this is kind of parallel to this one. So this is a forward difference scheme. You can also approximate it with the different this is backward difference scheme. You can also take something like 1 point before and 1 point after, and then approximate this. It's something like this, which is kind of parallel to the original one. So that would be central difference scheme. All of these are different ways to estimate the same slope that we are trying to get. You can come up with any arbitrary scheme which says some linear combination of different function values that will estimate the slope of this line. The whole point of this exercise is to show that there can be different ways in order to get the same estimate of the slope. Once we estimate the slope, what we are trying to do is find the values of these functions. So we will do this for each and every point, and then we will get a set of equations. The set of equations is what we will be trying to solve. So what we are essentially doing is we are converting our PDE from original PDE into something called a set of finite difference equations. So this is, if we expect them to be linear in nature, if they are linear, then we can use a linear solver to solve those set of equations. So how to do that we'll be discussing in the next week. So this week the whole point is to convert, given a PDE, how do we convert it into a finite difference equation, a set of finite difference equations. That is the whole point of this particular week of lectures. Now as we said, like there are multiple ways in which can I discretize the same function. So how do we know differentiate between, what is the difference between each of these different schemes? So there comes the definition of an order of accuracy. So when we try to discretize a PDE, let's say I have a PDE df dx is the original analytical term. I have a function, I can calculate, if I know the function analytically, I can calculate this differentiate, like I can differentiate it and get the exact value of df dx. Similarly, I can also do something like the one that I told before. Let's say we use a forward scheme. This is an approximation. So how close is this approximation to the analytical value? The metric that says that closeness is what we call order of accuracy. And that, how we decide that is, as the difference between this xi and xi plus 1 and xi gets reduced. So if in my original domain, so if this is xi, as xi plus 1 goes close to xi, the rate at which the actual value of the slope approaches the analytical value is what is defined by order of accuracy. We can estimate this from Taylor series approximation. Again, from Taylor series expansion is valid only for continuous functions, and for that particular assumption which we have,
I mean, kind of a different question I want to ask, a little bit I don't know. So what you're saying is we have the, like, say that I will take a PDE which is first order.
Okay.
There is no second order. Say you take second order PDE, okay, and I will take a to 3 point stencil final difference, which we'll discuss, I think, if I'm not wrong. Like d square is equal to rho square is equal to a square.
Okay, one second order. Okay.
So my question is, since my PD is only second order PD, right?
Yes.
And my scheme can accurately predict second order. Let's say that it is like my PD doesn't go beyond second order. Okay. Do you think this final difference will give you like exact answer as analytical with that given case? Do you understand what trying to ask?
No, not clear.
Um,
Like let's say I have d square f dx square,
yes.
and you're trying to use a 3-point stencil. So let's say you got something like
Equal to zero. Equal to zero. Equal to
oh,
zero.
your
This
governing equation itself is Laplace equation.
equal to zero. Yes. Ha ha ha.
Okay.
Equal to zero. So any f which is like if it is less than x square, so it is equal to zero, no? Like if f is less than, like if it's x, in the derivative will be equal to zero, right? If say that the solution is x, f equal to x,
If the solution is f equal to x,
then our result is zero, right? At each
yes,
point, the governing equation says that it is zero.
yes,
Okay. So my question is, now say that I take f equal to x cube.
okay.
Okay, and now at each point
It
it
is
has
not.
some solution. Yeah, if that is the solution. My question is, now say that my finite difference scheme is able to is third order,
Okay.
because now you said order of accuracy is one, like that's what you were trying to say, right? Delta x or something. Now you say that my finite difference scheme's order of accuracy is 3.
Hmm.
You think we are exactly solving this? Sorry, I don't know if I can ask these questions.
It
Maybe
doesn't
we
have
might
to be
continue.
always, right?
It has to, right? It should be able to solve it exactly. There's no error order condition, right?
So you're basically saying that your function is such that if you take it's a second order derivative is zero, so it is solving Laplace equation, but the
Yes,
function
and I'm
has a
giving the
cubic
solution.
polynomial.
F is x cube. Say that x cube is the solution. Yeah.
F for x cube is solution for some differential equation. So this is a solution for some differential equation, and you're trying to say that I want to discretize the differential equation in such a way with a finite difference scheme which is third order accurate.
Yes, yes, yes.
So you're saying then I'll get an exact solution. Is that
We
what
lie,
you're trying to say?
we lie, not.
Okay.
I.
Yeah, okay, let's kind of uncouple two things here. Order of accuracy has nothing to do with whether we'll actually get like what I'm trying to say in order of accuracy is when you have a stencil, as you try to reduce the size of the stencil, the rate at which you can get closer to the actual solution is what is mentioned by this order of accuracy,
Um.
right? So as the limit
So
xi plus 1,
are you not commenting on the order of function you are approximating, like x
no,
or x
no,
square?
that is different. I am not commenting anything on that function. As
What
in
is
general, we do not know what the function is going to be, right? Function is an unknown. It cannot be polynomial in general also, which we do not know yet.
Yes, yes. No, no. My question is then, which part of numerical methods concept do you think that goes in? Because that's what we do, right? We say that we can approximate this thing exactly, like linear function, second order function, or approximate it exactly. That's
Yeah,
where we start.
for example, if you have a quadratic function, you can use a second order thing and it becomes equal to that. Again,
Yeah.
that is specifically for a uniform grid. Again, if you have a non-uniform grid, then that doesn't even also converge. So in general, we cannot
Non.
if you have a non-uniform grid, then what happens? How can you comment on that? Like,
Yeah, that is different. No, no, no. Let's not go to non-uniform. We're only dealing with single delta x. Okay, but okay, yeah, you can continue. Yeah. Yes. Yeah. Yeah, I'm sorry. I don't know if I'm interrupting. I can ask this
yeah,
continuous
no
question.
problem.
You can
Like
let me know.
this session is meant to be kind of a discussion. So if there is something that comes up, then either it's not like I also know
Okay.
everything, right? I'll also speak with professor or someone and then get back to you next week.
Cool, cool, cool. Okay.
Yeah. So the point I was trying to make here is as the grid gets close, smaller and smaller, as this xi plus 1 gets closer to xi, then how close is our approximate becoming like the original approximate is this. So as xi plus 1 goes closer to xi, how this line will keep shifting towards this line. So this line, so this is my slope, this is my actual slope, this is the one that is estimated. As xi plus 1 gets closer and closer, this line will actually get closer and closer to the original one. So for a unit, so the rate at which this gets closer is defined by order of accuracy. So this we will estimate from the Taylor series expansion. So if I have for this function f of x, the other terms are second order.
Hey, but
Yeah.
now you're talking about it. I want to I mean, not maybe after some time we can verify. We can take simple x square function
Yeah, I have that as a problem.
and
Yeah, I have
yeah,
that
we
as a
can take
problem. Yes.
and we take second order
Yes,
second order
yes.
system, and we can say are we approximating using this test stencil exact value? Like we can take
Yes,
x
yes, yes. I
plus
have that as a
j.
problem. We'll discuss that in some time.
Have it? Yeah, then that will be much more
Yeah.
clearer. Cool.
So from this, if you were to approximate f prime of x, plus some terms which are delta x square, so that would become delta x. So this particular scheme is of the whatever is the power of delta x that we are going to get here define is, let's say this is here it is 1, so this is first order accurate. So what this means, if I am using a stencil size of say delta x equal to 1 unit and I got an error of particular value, and if I reduce the stencil by around delta x by 2, then the the error between the actual analytical value and the one that we are that we are getting from the grid is going to reduce linearly, so it is going to also reduce by half. So that is what we meant by order of accuracy in this particular case. But in reality, the problem that we encounter is we do not know the analytical value always. Like for all solutions, we do not have the analytical value. So all we end up doing is we'll only get the numerical values, that the approximates that we are getting here. Yeah.
Yeah, I mean here I think you can clearly verify that. Say that you take f of x, assume that f of x is x.
Okay.
So in the first equation you wrote, f dash x will be 1,
Yes.
right? And we are exactly approximating linear function, right? Because when you take delta
Yes.
x, so
Yes.
that's what. So if you take, sorry, I mean not what. Similarly, if you add f double dash x, if
Hmm.
you add that term as well, I think you're approximating second order functions exactly.
Yeah, that goes true for as long as you have a polynomial. Let's say I have
But
sin
but
x.
I mean, exactly. So sin x, that's the whole point. So depending on the function you're approximating, now say that you are approximating linear function, second order function. Sin x is combination of like it's a 1 plus x. It's a different thing. We're not talking about that. But I
Yeah,
got the idea. I
yeah.
understood.
As long as you take polynomials, then it goes in that way, right?
True. That's what.
Hmm.
Exactly. But there are some functions where the function like there are some derivatives, some PDEs where you say pressure is only itna order, only till this order. So there we can rely on this, and hey, you know what? It has to have exact solution back. But usually that's not what happens with our fluid mechanics equations.
Like, can you give an
Yeah.
example or something where that happens?
You can take Laplace equation.
Okay. Let's take steady
Probably
state heat conduction equation.
Yeah, and probably set some boundary conditions such that you know the exact analytical solution
Analytical
back.
solution. Okay.
Make sure your boundary conditions such that you know the analytical solution. Now say you take delta Laplace is nabla square phi equal to 0, right?
Hmm.
Now say that I will say my phi is equal to x plus y.
Okay.
Okay. Now phi is linear in x and y, right?
Yes.
I think there is a solution. So when you take nabla square x and you disguise it into using first order of accuracy 1, like if you do that discretization and you solve it,
Hmm.
you will get phi to be exact on the boundaries or everywhere it is like exact value, you will get it back. But if you take phi as x cube y plus y square x or y power 4x, okay, and if now what we will do is we'll take our stencil. Like now we will do second order f of x. Second order finite difference method.
Okay.
Since it cannot approximate it exactly, or even if you take x cube plus y cube, there will be an error of that second order ke baad f double dash f triple dash x utna error you will see at each point.
So let's say if we get an error and I try
Yes.
to reduce my stencil size,
Yeah.
then what would happen? It would have to reduce, right?
That is of course, yes,
Yeah.
yes. But did you
Yeah,
understand
I
what I'm
understood
trying to
what you
say?
are trying to say. So we would actually
Yeah.
get an exact solution for certain functions as long as your order of degree matches with the accuracy of your scheme.
Yes, if it is higher than the order or equal to the order of function which we are dealing.
Yeah, yeah.
So,
I
do
got
you
what
agree
you are.
with me?
I, I like as for these examples, I can agree, but I do not know whether this holds for in general for all the cases or not because I'm still not convinced why it actually happens.
Okay, okay. But at least this example
This
seems correct to
example seems
me.
correct, yeah. Example seems
Yes.
correct, but I cannot generally conclude directly. I'll
Of
get back
course,
to you
yeah,
on that.
yeah.
Yeah.
Sure, sure, sure. No problem. Yeah, yeah. Good.
Yeah. So the next one is how do we do it for an arbitrary stencil? So let's say in the previous case, I've already given you that this is the form that we'll be using. In general, what we'll try to do is, let's say I want to approximate some derivative f prime at a given point I as a function of some grid points, something like this. So some linear combination of these grid points, and I need to find the values of ABC. So how do we, the general way to go about this is we construct something called a Taylor's table. So what this table has, let's say we'll write all the terms here. And we construct for each value. Say for at fi is basically the value of f at that given point. We do not have any f prime or f double prime or so terms. Let's say fy plus 1 is basically fi plus delta x by 1 factorial times f prime, and so on. So the I plus 1 term, I write the coefficients here. So I have 1, this is 1 by 1 factorial, 1 by 2 factorial, 1 by 3 factorial, and so on. Similarly, I can do for I plus 2. So instead of delta x, for when I write I plus 2, it will be 2 delta x. So I'll have 2 by 1 factorial, 2 square by 2 factorial, 2 cube by 3 factorial, and so on. So the idea here now is we write this equation. When we write this equation, the coefficients of similar terms have to be 0. I mean, if I write it in the general form, so f prime is basically a into fi is f or p into these coefficients, plus the last one. So we try to equate the coefficients on both the sides. So we do not have any fi term on the left hand side. So this will be a plus b plus c. For f prime, we have, just take the delta x to the other side. And for f double prime, we have b by 2. So we have 3 equations and 3 unknowns. So this is the max that we can go ahead with this particular scheme. So alternatively, from the Taylor's table, you can directly write the equations. So just multiply this with the corresponding coefficients a, b, c. So a plus b plus c equals to 0, first equation. For f prime we have b plus c by b plus 2c equals to 1 by delta x, and for f double prime a into 0 plus b by 2 plus 4c by 2 equals to 0. So when you solve these three equations, we'll get the values of a, b, c. And whatever is the term that will be remaining of like we have solved up until f double prime. So since we have only three coefficients, we can only take three equations. So the one that will be remaining is delta x cube, and we have a 1 by delta x here. So that order of accuracy for this method will be of delta x square. So in general, you can construct for any other values as well. So if I want third order accurate, then I will have one more coefficient depending on. You can also take a stencil of different sizes. Instead of I plus 1, I plus 2, you can go with I minus 1, I minus 2 or something. So construct a table, and from there you can use this. But now we can always use the library. Say if you are using Python or something, we have SymPy or something from which use the symbolic array and thus directly give us these values of ABC, the coefficients that you can get. This is how you construct this. Again, this is assuming that we are considering a uniform stencil size. So which means this delta x I have taken out here is kind of constant. So that is the case for uniform grid. We can also have a non-uniform grid, but like there are several flows in fluid mechanics. We especially deal with boundary layer flows. Whenever we have wall bounded flows, we have boundary layers. And when you have a boundary layer, so if let's say if you take a forced convection problem, the velocity at the wall has to be 0, and let's say we have the classical glaciers boundary layer kind of profile. So the velocity gradient here will actually be steeper, and in order to capture those gradient accurately, like as you was pointing out before, like depending on the resolution you are going to have here, you are going to like when we say when it is wall resolved, what we were expecting there is our finite difference scheme. Let's say you are using some scheme which is approximating with a line. So this is how we are approximating the function. So it is consists of series of lines, while the actual function is of some different shape. Let's say it is something like this. So only if these lines are like if these points are closely spaced, I will be able to capture all the different gradients that are possible in the actual profile. And in order to do that, we have to have very closely spaced grid points along this direction. So let's say this is my y direction. So along the y direction, my grid points should be placed very close to each other. But if we keep placing everything very close to each other, then we would have so many number of grid points. So what we do instead is we define something called a non-uniform grid, where you initially start with a very low value of grid spacing, and as you go farther and farther, you will keep increasing the grid spacing. So if I were to draw a line, so this is my y-axis. So it is my, let's say this is my first point, and so on. So you start from some grid spacing delta x. So instead of being equal, you will scale it by a factor of r, and you keep doing it in geometric progression. So depending on the value of r, you will usually for boundary layers and flows, we actually use r close to around 1.2 for forced convection. If you are dealing with some natural convection problems, then it can actually be little lower also. But the problem here is unlike the uniform grids, the difference scheme actually changes here. So if you see the same table that we have taken before, if you consider the same table, so now in place of delta x for the I plus 1 and I plus 2, from I to I plus 1, let's say this is my I, this is my I plus 1, and this is my I plus 2. So if I to I plus 1, it is delta x, so this will be r times delta x. So for the second one here, previously I have just the coefficient 2, but now there will be an additional term that is getting added because of the expansion coefficient. So I'll have an r here, I'll have an r square here, accordingly r cube and so on. So this additional term will actually affect change the values of ABC that I'm able to get. So if I write the equations here, so this will be a plus b plus c equals to 0, first equation. The second one will be b plus 2rc equals 1 by delta x, and then the third equation is b by 2 plus 4r square c by 2 equals to 0. So now these equations have changed depending on the value of r. The values of a, b, c you are going to get are going to change. So the difference scheme is also kind of changing depending on the value of r here. But the way that we solve, like in order to get this equation, is remaining like as long as you familiar with Taylor table and be sure to make these changes appropriately, then you are going to get the equations correctly. The most important one is the error and accuracy that we are discussing. So when we have a PDE, we are converting from the PDE to a set of finite difference equations like the one that I have shown before. Is, let's say we have df dx. Instead of df dx, we are writing it as on our discretized kit something like this. So when we do this thing, we are obviously introducing some, this and this are exactly not equal, so there will be some error here. That is what we are terming as truncation error. But as you can, and this truncation error should actually ideally should go to 0 as the stencil size becomes smaller and smaller. So as xi plus 1 tends to xi, this value should actually approach the df dx. So when I have a differential equation, so let's say we have our continuity equation, or for that matter let's take some Poisson equation, uxx equal to some function f. So when we have some equation like this, we will discretize this equation. So the discrete form of this equation would be something like, for a double derivative, so let's say after on the discretized mesh, this is the equation that I am going to get. So the difference between this equation and this equation is what we are calling the discretization error. So this will be my discretization error. So what we expect in general is the difference equation, this is my finite difference equation, should ideally approach the value of PDE as the mesh becomes finer and finer. That is what we are called consistency. If FDE approaches the PDE as your mesh gets finer and finer, you call it a consistent. That particular scheme is called a consistent scheme. Once we have a consistent scheme, so we write this equation for all the different grid points we have in our domain. So then we'll have some set of equations, we will solve the set of equations. So you need a solver to solve these equations. So depending on the, depending on your problem, you can end up in a linear solver, or some cases we have non-linear solvers also. But once we have the solver, we will get a solution. If the solver is giving you a stable solution, by stable I mean that the values are actually not, okay, let me define it in a different way. So we have not discussed solver set, so I'll skip the stability for now. But the idea here is, let's say you get a solution. You have a set of equations and you get the answer to those set of equations by using some solver. And if that answer, we'll call that answer as the finite difference solution. And then I have a PDE solution. This is my solution, the exact analytical solution, and this is a solution that I am getting from solving this finite difference set of equations. If you are having a scheme from which you are getting a solution and you are having a scheme which is consistent, then you are known to have something called convergence. Convergence happens when you have a consistent scheme. So your finite difference equation reaches the partial differential equation when your grid size becomes smaller and smaller, and also you have a stable solution. When these two conditions are satisfied, then you have convergence. And when you have convergence, you can rest assured that the solution you got from finite difference will be the exact solution. And we have other errors, like this is the discretization error because of because you have discretized your domain into finite set of points instead of having a continuous domain. We also have another error called round off errors. So these are the errors that are coming because of your fixed precision of your particular computers you are using. So we will discuss that in the next week. We'll actually take up a problem where we'll actually get these round off errors and see how they'll actually come into the problem and what they can do. Those kind of things we'll discuss next week. But the idea here is to understand that there are several reasons in which your actual solution might be different from the analytical solution. And in order to be sure that the solution is actually reaching your actual exact value, we need to ensure that we are using a consistent scheme, so that as the grid becomes finer and finer, your solution approaches the PDE solution, and you also need to use a stable solver. How do you decide stability and what are the different criteria for that is again something that we will discuss in upcoming lectures. Hope there are no questions up until here. So the theorem that goes into this is the Lax equivalence theorem, which says that whenever you have a scheme which is stable and consistent, then we are going to have a convergent solution. At this point, I'm asking you to take this statement as is, and we'll get into it when you solve some problems later. Now coming to the one that we were discussing some time back. So what happens if we have a uniform grid and we use a central difference formula? For which of these equations would it be an exact solution? So we were discussing some point before. Let's say I have a function f of x equal to x square. Let's take a quadratic function, and we know that the derivative of this is 2x. Now let's say I'll use a central difference scheme. So in central difference, we'll approximate this as, so if I were to draw on the grid, so this would be this value minus this value divided by
Quadratic.
Yeah, this is quadratic. So if my function is x square,
Square should, yeah.
x plus delta x.
That's what I was talking about.
Yeah. So this b whole square minus a minus b whole square. So the approximate derivative that I am getting from this versus the one that we got from the analytical solution are matching with each other. So on a uniform grid, again this is on a uniform grid. When we use a central difference formula, then the quadratic is actually, for a quadratic equation, both the approximation as well as the analytical will actually match with each other.
I think it has nothing to do with the grid spacing.
Okay.
Ask me.
Let's say
Right?
if we have.
What do you think?
Okay, let's just try it out then. Let's say if the grid spacing is not uniform. So.
But it has to.
No, we can just try it out, right? So you have.
Yeah. We'll take 3 points. Delta x by 2 and delta x.
No, you want to take it like x plus r times delta x by 2 and x minus delta x by 2.
What is r?
The one that determines the non-uniformity. Like, just don't want it to be uniform, right?
I mean, no. We'll take
r. Okay, you want to take
delta x.
Sorry, you want to take?
One is plus delta x by 2.
Okay.
The other one is minus delta x.
Okay.
It's very like one simple case.
Yeah, so can we quickly compute this one?
Okay, so we will do
x plus
say we want to approximate it 1.
It's central difference, right?
Yeah. Delta x common.
So I'm getting 2x plus delta x by 2. So this is the residual that you are getting, right? Sorry?
It should be 2x, no?
Yeah, it should be. So this is the residual that you are getting because of that.
Delta x, why are you getting delta x in the first place?
You have delta x here. So did I do something wrong in the calculation?
Yeah, you should not get delta x, no? Am I right to
Why?
assume?
I have delta x here, right?
Okay, you get delta x square
So I have a minus
the
here. And then this will turn out into minus.
delta x cancel. Okay, delta x square. Okay, something I will try this out. It's interesting.
I think calculation is correct.
No, 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 no. This is not how we should look at it. No. What is this pencil formula we have for central difference of first order derivative?
So if this is my I plus 1, this is my I,
Yes.
this is my I minus 1.
Yes, to find the derivative at I and on a second order difference, the formula or the function approximation is I plus 1 minus I. This is formula, no, like three points by del. That's what we should use. We should not use direct
Okay,
formula.
you are saying that, okay, let us
What
derive
happens?
the non-uniform grid
Huh.
equation and then solve with that, then the order of accuracy will match. That's what you're trying to say, right?
Exactly. So what we
So
should
you're
do is
saying
to
we'll
find the
solve this
difference.
equation,
Huh.
but with I
For
minus 1.
a specific problem with different delta x values, and we will
Yeah,
get a
if you
value
know that particular grid, then it should match.
equal
Yes.
to analytical. Equal to analytical value. I will do that. I will do that.
Yeah, it should match then. I
It should
mean,
match. No, delta x should not really matter. I mean,
no, it
because
should
it was.
match because we are actually solving for that. So when you solve this Taylor table, you're essentially making sure that the other terms are actually going to 0, right? So you are
Mm-hmm.
forcing that in a way. So it will obviously match when you do that.
Obviously, okay. Okay.
Yeah.
I mean, dangerous words to use at least in
Oh,
my.
okay. Okay.
Anyways, good. Yeah, yeah.
Yeah. So are there any other questions from anyone else?
No, no, no. Let's move to the
Okay,
next one.
let's move on to the next one. And then we have the forward difference operator. This is more of like a memory question at this point. So when we have a forward difference operator, which of these is true for them? So for a forward
D.
difference on I plus 1, so you have fi plus 1 minus fi.
Okay.
Yeah, so this is where regarding the order of accuracy, all of these are kind of memory questions from previous years. So which of these is true for a grid size of delta x? So you just need to know, like for a central difference, forward and backward difference, what are the order of accuracies? So central difference is quadratic in nature, forward and backward are linear.
First option is right.
Yes. So this has to be delta x.
But this things gets interesting if we are solving for an implicit. If you're doing for implicit form. So for
But we'll
using explicit. Boliye?
no, but once we go into no, next week is elliptic, right? Next week is elliptic equations. Then we can actually do some problem. Then we can actually plot and
Right.
see whether it actually converges in linear or not.
Yeah, no, I mean, exactly. So as far as I know, when you go for implicit problems, it mostly reduces the delta t, this delta t kind of thing.
Yeah.
But I think it has nothing to do with the order of accuracy, right? If you do implicit or explicit, it should not really matter.
Yeah, because the one that we are discussing here is truncation error, right? This is just about the derivative
Yeah,
that we
order
are
of
trying to
accuracy.
approximate. It has nothing to do with the entire differential equation, so
Yes.
shouldn't matter.
So yeah. So even if you do implicit, the answers stay the same. So
Yeah, that would be
okay.
different. That I think you call that discretization error or something. It wouldn't be called as truncation error.
Okay. Okay. Okay.
Yeah, now we have something to make your hands work. So we have a function of this particular form using a step size of so and so. Calculate the double derivative of the function at x equal to 0.5 with central difference and compare it with an
Hmm.
exact value and see how much the error is.
Exactly.
First thing is you write, okay, here I have written as del square, but ideally this is a first order equation. I mean, it's not even a partial differential equation, so del square is basically replaced by d squared f by dx square, and we'll approximate it with central difference. Again, it says that using a step size of delta x equal to 0.5, so we're assuming it is a uniform stencil. So when you have a uniform grid, your x is 0.5 and delta x is also 0.5. First you write the equation. So we need to compute the value of f of x plus delta x, which is f of 1, x minus delta x divided by 2 delta x is 2 into 0.5, which is 1. You can quickly compute this
You should
values.
do it x. Okay, f of x. Okay.
Right.
Cool.
This would be one way. This would be, from this you would get the finite difference form, and then you will also have to calculate the analytical solution, which will be,
yes.
just take the derivative of that. And then substitute x equal to 0.5. Let's say this is equation 1, equation 2, and we need to get an error. So how do we find the error? Here is the value that you are getting minus the actual value divided by actual value into 100, or the other way around. The one that I reported is anyways modulus, so it shouldn't matter. But as long as you make sure the denominator is the exact value, you should be able to get the answer, one of these. I don't think there are any problem in calculations.
Yeah, good.
So now this is again using Taylor's tables. Let's say we want to approximate with I minus 1, I and I plus 1, again with a uniform step size. You have to, how do you find the values of ABC? So we'll first construct the Taylor table. Since there are only 3 coefficients, I would have been needing the third one. So for I minus 1, for I plus 1, so this would be my ABC. All we have to do is write the equations. A plus B plus C is 0. We have minus A plus C equals to 1 by delta x, which is 0.2. For now I'll just write it as 1 by delta x. And then third one is A by 2 plus C by 2 equals to 0.
We can do forward difference, backward difference, and sum it up, and that's the typical way of doing. Like this looks like that second order from. Yeah, this is also.
Yeah, but this is a general way, so this works for any case you can take. So in exam, if something comes up, you don't have to be so creative. You can just follow something.
Yeah, true.
Yeah, solving these equations is kind of straightforward now, but we'll also see some solvers from next week. Of course, here there are 3 equations, so it is straightforward. Let's say I want to derive, say, 8th order equation
What do
or
you
something.
mean by solvers?
This is actually a set of linear equations, right? That you have to solve. We'll basically in Python, if you use NumPy or something, we'll just see how to use that one. That's it.
Do we do any like Stokes or something like that?
Elliptic equations. Next week is elliptic equations.
Okay.
So maybe I'll start with heat transfer equations first. We'll go to Stokes a little later, right?
Okay.
Advection comes a little later.
Do you do Stokes in finite volume as well, like by the end of the
finite volume is towards the end of the week, end of the sessions.
Yes. But
so I do not know Stokes? If the time permits, then we'll actually solve. Otherwise, I'll take an extra session towards like after week 12. So depending on how many students are there, we'll take up that one.
Just a spoiler, if there are not many people, I will push you to do Stokes first. Anyways,
it's depending on how many students are there.
Yes. Stokes seems much more useful and very applied. And
for particular to CFD.
I want to ask you, so you'll do speed equation next week, right?
Yes.
Are you gonna do implicit or explicit?
It's a steady state equation. We will start with Thomas algorithm, so which is kind of it's a pseudo thing. I wouldn't call it implicit.
Okay, fine. Okay. Heat equation you have the dou T by dou T, no?
No, elliptic equations. So the structure of the course is like first you start with elliptic, then you go to hyperbolic, parabolic. So first we start with steady state only.
Okay, good.
Yeah, so solving these equations again, I'm just skipping that part. I'll post the solutions of this in the sense that you'll know the answers like when you prepare for the exam. Yeah, all of these are in the same form. So obtain a third order accurate scheme. So here the difference is we are explicitly saying that I need a third order accurate scheme. So what are the values of alpha, beta, gamma and delta?
Yes.
So how many equations do I have to take? For I minus 2, this will be minus 2. So since we are taking up like 4 unknowns, we'll be taking up to 4 terms, and the one that will be remaining here is delta x to the power 4. And because we are trying for fx, so which will have a delta x, so that the order I will be getting here is of third order, because the term that will be left over here is, I'll just write it as, so this one will be of delta x to the power 4. So when I write my equations, so let's say if we write our equations, for f it will be for f prime for f double prime for f prime this will be equal to 1, for f double prime this will be 0, and for f triple prime so this alpha is going to be something like 1 by delta x or something. So when we have these equations written, so all these coefficients will be of like will have a term of 1 by delta x in them, and the one that is left over is delta x to the power 4 or something. So if we divide this divide with delta x power 4, the order of accuracy is going to remain as delta x cubed. So if you were trying to get an equation for f double prime or something, then we'll have a delta x square term. So the one that the term that is going to come next divided by this particular one will give you the order of accuracy. Now again this is kind of not symmetric in the sense that we are having I plus 1, I minus 1, I minus 2, but instead if we add one more one, I plus 2 or something, then you will see something happening that the terms will actually get cancelled, and you'll get an additional degree also, like additional degree of accuracy as well. That I have not covered in this particular problem, but you can look it up yourself. So let's say instead of I minus 2, let's say we take only I minus 1, I and I plus 1, then these terms will actually look similar, like they'll get cancelled when you try to solve for f double prime or something. Maybe I should have taken an example of that one. Okay, does my word make sense, or are there any questions?
Yeah, no questions.
Okay. Yeah, no, this is again, all of these problems are on the same thing. If you know the Taylor table, you will be able to solve all of these. So instead of solving for each and everything, you have to just solve for the term C. So the construction goes in a similar way, but now we are solving for f triple prime. So have f. So f triple prime is what we are interested in. So we have I term, I plus 1, so the equation that we are going to get is So just take a dot product of these two matrices and then equate it to 0. So equate it to 1 because we are solving for f cube. The coefficient here is 1. So this will be minus 5 into 0 plus 18 by 6 minus c into 8 by 6 should be equal to 1. Solve this to get the value of c. This is again a straightforward one. Yeah, all the problems are similar. So let's say if you want to expand this function about x naught in Taylor series, then the fourth term in the expansion is given by. So general form is f of x plus some delta x plus, let's say, n equals to 1 to infinite. We have fn, this is the derivative of f at that particular x times delta x to the power n by n factorial. So this term asks the fourth term in the expansion. So this is the first term. So the fourth term will have n equal to 3. So if you substitute n equal to 3, so that will be delta x cube by 3 factorial into del cube f by del x cube evaluated at that particular x naught. So instead of delta x, we are having minus 2 delta x here. This will give you minus 8 delta x cube by 6 straightforward substitution. As long as you're like, if you forgot the Taylor series expansion, then we can't do anything about it. So if you know the Taylor series expansion, it should be a straightforward one. Now let's say we have a function like e power x using a mesh increment of delta x equal to 1. F prime of x is very similar to the one that we solved before. Calculate the analytical value, use the finite difference scheme, compare these two values and report the error. So the analytical one is f prime of x is e power x at x equal to 1 is e. Similarly, the finite difference form using this particular scheme, delta x is given as 0.1. You can get this value. Let's say this is 2, this is 1. This gives you the percentage. So you can also try it out, like instead of delta x equal to 0.1, if you use 0.001 or something, so you can plot it for different delta x values. Or let's just plot the error. What we would expect when we are using forward difference is a linear plot. So we should expect like a straight line. So obviously delta x equal to 0, error should be 0, but will not go till there, because as the delta x becomes smaller and smaller, your round of errors also will also come into picture, which are not shown here. But the idea here is we should expect the error should actually go linearly with delta x. Are there any questions? These are the questions I have in this syllabus from the last year problems. If you have anything else to discuss, we can discuss, or else we can end the session for today. To summarize, we started out with the Taylor series expansion, and then we discussed different finite difference schemes, first order, second order, and what is order, sorry?
Nothing from my side.
Yeah, to quickly summarize, we started with Taylor series expansion. We thought that any function value from a given value, we can extrapolate to a nearby value using Taylor series expansion for a continuous function. And we also discussed different finite difference schemes like first order, second order schemes like forward difference, backward difference, central difference, and we discussed something called a Taylor table, which can be used to construct your finite difference scheme of whichever order you want. And depending on the stencil you choose, there are again two kinds of grids, either uniform or a non-uniform grid. And eventually discuss the concept of error and accuracy. Error is when you have a finite difference, the analytical solution. When you discretize it, you are going to have something called a discretization error, because instead of solving it on a continuous domain, you are considering only a certain fixed number of points for which you are seeking solution for. Then we also discussed like the differences are also approximated in the finite difference form, so that leads to a truncation error, which is, and the estimate of that is, we got that from Taylor series expansion. And the concept of consistency, which says that as your stencil size gets smaller and smaller, your finite difference equation should represent your actual PDE. When that happens, you call that a consistent scheme. When you have consistency and a solver which will give you a stable solution, then you are going to have something called convergence. That means the solution from your finite difference scheme is going to be close to the actual exact solution. That is the Lax equivalence theorem. And then we'll discuss some previous year problems. I think there are no further questions. And to those of you who have sent me mail regarding the Google Drive link, these slides, whatever we have discussed, will be uploaded on the Google Drive link. That is shared with you. You can find it in the problem solving session. When you click on this link, you will be redirected to a Google Sheet where you will find the recorded session YouTube links and the Google Drive link as well. It was not accessible last week, but it was updated now, so you can find them now.
Okay,
Yeah.
so we will discuss coding next week.
Yes. We'll solve some elliptic equations. So maybe Laplace and Poisson will take, but mostly linear equations.
Okay, if you have time and if you can, if you have time, if you want to discuss unstructured grids in FDM, do you do unstructured in FDM or FEM?
FEM is much more amenable for unstructured.
Unstructured, okay. I mean,
But
if you
then we
have
also
time,
have to deal with dealing with the mesh also. Like you also need to do, like when we deal with unstructured, the problem that comes is you have to keep track of all the points and stuff.
yeah, the neighbors and everything, is it?
Yes, like coding all of that from scratch would be like it would be not that relevant for the course. We can either do one thing, is instead of directly dealing with the mesh itself directly. So what we so I have actually taken up unstructured. There is another course called finite volume for computational fluid dynamics.
Yeah.
On NPTEL, you can find those on my YouTube channel. Where we have actually taken an unstructured grid and solved it. It's not actually completely unstructured. I would say it's more like a non-orthogonal mesh. I wouldn't say it is unstructured. It's still structured in a way, but non-orthogonal. So you can understand what angles.
Things like there's this. I mean, some of the I think the main differences would be how would you apply boundary conditions and this flux computation.
Yes.
That's the main thing. That's the only thing is difference. Is difference, right?
Yeah. So instead of focusing on this connectivity and stuff, it's still structured, but you will understand what happens when non-orthogonality comes into picture. Those problems are discussed in that particular channel.
We can discuss it, but if you feel like talking about it, you can talk about it in this course if you can. I mean, there's no pressure from my side, but I will be happy to be in your audience.
Okay? Yeah, sure. Towards the end of the session. Thank you.
Hello, sir.
Yes.
So actually, I'm in second year of my mechanical engineering, that is in fourth sem, and hello.
Yes.
Yeah, and I'm trying to learn CFD. I'm focusing on kinematics of flow, as my fundamentals are yet to be completed. So I'm focusing on them, and then I will slowly head towards the computational methods. So, sir, what should be the specific roadmap for me?
Okay, you have not done a fluid mechanics, only the fluid dynamics course, no fluid dynamics course as of now. Like you have done any course which says you the momentum equation or Navier-Stokes equations yet?
I have enrolled for the introduction for FM.
So you're yet to do that particular one course, right?
Yeah.
Okay, maybe it's better if you discuss this after you complete the course. So take a course on fluid mechanics, so as in say the Navier-Stokes equations, where you derive the Navier-Stokes equations. And then better if you can take a numerical methods course also, wherein you discuss different kinds of solvers, or if you're familiar with linear, you would do that as a course in mathematics, right? Linear programming.
Yeah.
Linear algebra or something would be there.
Okay, can I weigh in?
Yeah, sure.
Okay, if you can't wait and if you want to have like easy, I want to get an introduction of this numerical methods or CFD. You should look at this 12 steps for CFD. Okay, this is by Lorena Barba. She's she's a professor in the US. She does this entire course in Python. She starts from difference, like whatever this course is being taught. So she starts at that point and she eventually solves lid-driven cavity, and pipe flow. Like whatever we solved at the end of the fluid mechanics course, like quality loop and everything. But she does this using finite difference and Python. So you can check it out if you want to. It's called 12 steps for CFD. Okay.
Okay, sir. Certainly, I will search for that. Actually, my motto was to become fundamentally strong, and just I just wanted to understand everything happening in fluid mechanics by computers. So, just for sake of curiosity and to learn, I just joined this course.
I mean, to be really, if you depends on fundamentally strong, maybe you want to write a new answers. You know, it takes something like you should do a PhD or something to be at that level. Yeah.
Yeah, what I understand. Okay, so maybe you'll be able to solve real world some problems or something instead of focusing on the numerical solver, just on how to get the right boundary condition and stuff like that. I think that would be what you should be aiming currently at after your fluid mechanics course.
Sir, actually, if I completed my fundamentals in 1 month, so how much time will it take to master, like just to understand every type of flow and every phenomena in fluid mechanics?
Okay, that is kind of
Dude, there are a lot of phenomena. Sorry, Prasad, I'm interrupting, but this actually, there is a lot of flow. Okay, depending on the Reynolds number, you deal with different kinds of flows. Okay, there is Stokes, there is the like then you have Reynolds number 100, then you have like turbulent, you have laminar, then you have like acoustics, which are very fundamental. Then you have ocean engineering, then you have shallow water equations. It's a huge thing, and like people do PhDs in a very specific topic.
yeah.
Like you
So
have
it's
you
actually
have
very
to
vast. We cannot actually pinpoint a time frame saying that you will be able to complete it in this time or something.
So you can't do everything in fluid mechanics. You can do it, but it takes like 10-15 years for you to do it. But you can start with something very simple such as lid-driven cavity or whatever Durga is going to teach in the next week, like heat equation. This was a very good starting point, and from there you can pick it up and slowly maybe use SU2, or you can look at the softwares called AMREX, AMREX, or Deal2 or Phoenix. There are these software packages which are open source and online. You have to install a Ubuntu system, a Linux based system, and try to run those codes, and you will slowly get into it. Yeah, it will take some time.
But yeah, it is good that you are doing. You are interested in stuff.
Yeah, actually that's true. Yeah, you
And
must
you
have.
can see that there are different phenomena, as he was pointing out earlier. You have different phenomena, and each one is a kind of you need a different kind of expertise for that. Like say in this course we are only focusing on laminar flows. Once you go to turbulent, there are other problems that, as we are discussing here, if you know the partial differential equation in itself, as you say, if you take the Navier-Stokes itself, you cannot directly solve the Navier-Stokes. We'll have to make several simplifications in order to make it something that we can solve. DNS is something where it is kind of computationally very too expensive, so we make so many simplifications. So it's not like, let's say even if you have ANSYS or something that is already available, so instead of focusing on the different numerical methods or something, you learn ANSYS, for example, how to set up boundary conditions and stuff like that, and then you let it simulate. It is going to use a model which may or may not represent your particular physics, and how do you know that what all physics is possible is a different thing. You get to know that after some experience of dealing with that thing. So we cannot give a time frame on that.
Okay, actually, what is happening is since I have started fluid mechanics, like my mind is bursting to simulate fluids. Like when I see water
Yes.
flowing through the like any rock, or like it forms a V-shaped pattern. So just my mind said that when I will be able to do these simulations. So that kind of stuff happening. So just I asked like how much
Ah,
time
okay,
will it
okay.
take?
So you, to get you started with simulation without even having to know something. So if do you have access to commercial solvers or open forms, like open source ones?
Yeah, open forms.
Okay, you have access to open source, like, and you can use them, open form or something.
Uh,
So
yeah, I
most
can
of the
use.
solvers actually have solvers built into them. For example, if you go with Fluent or OpenFOAM or something, they do not actually use finite difference. They use something called a finite volume technique. Even without knowing the finite volume technique, uh, it has some pre-existing solvers. You can tinker around to get something. Like you'll get some answer. The question is whether that answer is going to be representing your real physics or not. If you put that aside, you'll be able to simulate something. That is just to kind of give you a feel that like you'll understand, okay, these are the things I need to know. But you can start with, let's say, open form. Let's say you started with open form. Start with some simple case, like in your fluid mechanics course you will be solving for pipe flow, like, or you would also be solving like a channel flow. These are simple flows that you do in your fluid course, right? You can start simulating them in open form. There are already courses available for that.
Yeah. So I'm sorry,
What is this
I'm
one?
you can check out that link I shared with you, Mayur. So it is a software based on smooth particle hydrodynamics.
Okay.
So what we do in this course is find difference method. Okay, there are similar numerical methods, but it is meshless. Okay, you can install it like with a simple click, but you should know how to install it. It's little pain, but you can use ChatGPT to install it. Okay, then you will be able to run a lot of fluid mechanics problems such as droplet, dam break, flow path objects. You can even have rigid bodies. So you can do a lot of stuff in there. It is all they have a nice GUI. Once you install it, it is a nice starting point. But to understand it and change the code, it will take at least like 1 year if you are good at programming. So yeah, but this is something very nice to start with. But once you know how a software works, you can easily move to other software such as Prasad is saying, like OpenFOAM or something which you want to deal with stuff which are numerically accurate. Yeah. Okay. But with this software, you can do all kind of movie simulations you can possibly think of.
And to
Check it out.
also point out that you are going to have a multidisciplinary thing. So let's say you have not just the fluid, like in this particular course we'll only be solving Navier-Stokes. So that is also kind of, we will simplify the Navier-Stokes and then we solve that. So this is kind of a starting point for you. So let's say you completed the course, then you might have to deal with flows where you might be dealing with something that is going to interact with the solid. So there will be some structural vibrations or something, like your fluid is going to flow through something, and that is your the shape itself is changing because of your flow. So you'll have some kind of couplings also. You can also have viscoelastic kind of thing. Those are all different like other equations will come into picture, not just your Navier-Stokes. How to couple them and all of that. So you have to be kind of strong in some kind of math as well. So how do you solve PDEs? General math. So it's not just about the fluid part. So you can maybe try taking courses in PDEs or something, not the analytical ones, but the numerical course. Any course that deals with numerical solvers of how to take, like given a PDE, how do I solve it in a general
So
sense.
actually, for that purpose, actually, I'm doing MATLAB simulations of orbital simulations. So that is kind of teaching me the numerical solutions.
That no, but there you would be dealing with what, a function which is like any function which is only function of time, is it, or does it also consider other coordinates?
No, sir. Currently now, just for time.
Yeah, because as far as I understand, these things only deal with f as a function of time, and then you'll use some ODE solver, right? It's not actually a PDE; it's actually an ODE kind of thing, but you'll have multiple ODEs. Like,
Yeah, we have multiple, like for different equations for like gravity and everything, forces, whatever forces acting on the satellite.
yeah, okay.
So, will it help and do will like sometimes I feel like is it helping me like for that simulations I have to define state vectors and position vectors, and we also build RC planes, so that is helping me in that also. So will that simulations help me to understand the simulations of CFD?
The main difference in those things is you actually convert, like you basically solve it as you convert a higher order differential equation into a 1D differential equation of some higher dimension. That was the main trick you use in all those problems, which is something we will use a little later. But here there is another part also. We also have space coordinate.
Mm.
So we actually have a set of algebraic equations and differential equations.
Actually, just differential equations and numeric interpolations, just two things.
When you have a state space vector, right?
Yeah, state space vectors, its differentiation and the Runge-Kutta methods and all
Yeah,
such stuff.
which will also be here, but in addition to that you'll also have a set of linear equations to solve. So those will kind of help you, but the thing is all these things are already incorporated in these solvers. Let's say, yeah, Fluent or something will already have a solver, And the problem is you would actually use, when you are using that, you would use something of let's say Rangakuta or something, which is a second order, or you can also go to higher order accurate methods, right? But
Yeah.
in this course we will restrict ourselves to max second order or something.
Okay.
Why second order or something? Those are things you will understand little later once you go into the fluid, but those things will be little helpful here, not so much, but it's better to know that okay, you can relate those things.
Yeah, certainly. So,
But it's not
so,
like even without knowing that, those things will also be covered in this particular course as well.
okay. Uh, so, sorry for that, but can you please introduce yourself? Like means,
Yeah, myself, I'm Durga Prasad. I'm a PhD scholar in mechanical engineering, IIT Madras, and I work basically on CFD for in building energy simulations and kind of glazing systems where you have fluid flow in addition to some other complex phenomena.
okay, nice.
Yeah.
So, can you please give me the tips for like what will be the future scope for that? Like, I'm in second year, fourth sem of my mechanical engineering. Then I will like do this stuff, and then what will be the scope? Like some,
Maybe we'll take that off. This session is actually recorded. We'll take that off the session.
yeah,
You can
sure.
write out to me on my email. We'll
Yeah,
discuss that.
yeah, right.
Okay. You have any questions for this particular course, as in what to expect from this course or something like that?
Um, no,
No? Okay.
actually, I haven't explored that much. Just week one is halfly completed. So,
Okay. Yeah, I guess then that's it. We'll end the session for this week. We'll again meet next week, 5 to 7.
yeah.
Okay,
Yeah,
bye.
bye. Thank you for joining.